Good evening. Usually I do these in the mornings, but I was late today, so I'm going to go ahead and get this done. I apologize in advance now. You're going to be watching this in the morning, and you're going to have two lessons in the same day, and I'm just going to sit here and no excuses. Just going to go ahead and do this and get it over with. So the bell ringer today is on what we discussed yesterday and the day before, student activity sheet 4, which was on, in this case, we're talking about the different design methods, and we're also talking about how to find what's called a representative sample of the population. Okay, in the bell ringer, we talk about the population of 476 seniors in high school. And in that 476 seniors, 248 of them are female and 228 are males. How many females and males would you need for a sample of 50 seniors? So you wanted to sample 50 seniors out of that class of 476. You want to make sure you had the same ratio of females to males in the sample that you do in the population. So we'll take the number of females and divide by the number in the total class, find that percentage, and then multiply the decimal equivalent of that by 50 to find out how many of those 50 need to be female. And we'll do the same thing with the males. So the answer obviously is you take 248 and divide by 476, and you get 52%. On the males, you get 228 and divide by 476, and you get 48%. Multiply those decimal equivalents by 50, and you're going to get 50 times 0.52, which is 26, and 50 times 0.48, which is 24. And you know it's right because if you add them together, you're going to get 50. 26 plus 24 does equal 50. So, all right, good things. I am recording this off location. I'm not in my classroom today. I am actually in my hotel room at the Horseshoe Bay Resort in Austin, Texas. Actually, it's in Horseshoe Bay, Texas. It's a tennis resort, and I'm here for my my tennis convention. And so I'll be here until Sunday, and then I'll return. And then Monday, I've got my contractors. I told you I'm going to be taking care of electricity and building part of my house on Monday. So anyway, that's my good things. If you've got some good things you want to share with me, by all means, send me an email. Let me know what your good things are. I'd love to share with the students in these videos so they know what's going on in your life and not just mine. All right, so today's lesson is on histograms. What does this histogram in the graphical representation represent? We're supposed to describe the distribution as completely and accurately as possible with regard to center shape and spread. So this is a histogram of monthly salary as depicted in the title. This is the frequency of times it happens to have a gross monthly salary of that amount. So it's separated into $25 increments, 800, well, maybe not 800, maybe not $25 increments. Well, but there's 4 increments in every one. So I don't know, 800, 825, 850, 875, 900. Yeah, that's correct. Okay. So it's in $25 increments. We can say a lot of things about it. What's the minimum salary in this histogram? It's $800. What's the maximum? $1,500. So we have a spread of 800 to 1,500. That's your spread or your range. Okay, what about the shape? Is it symmetrical? Symmetrical or symmetry means that one side looks like the other. Obviously, this side has 5 peaks all together, and this side, if you count them, has probably about 12 or 15 peaks, or little bitty tiny ones too. Okay, so in that case, the deal is this. It's not symmetrical because the two sides do not look alike. All right, so shape, we would say, yeah, it's not symmetrical. That's how we would describe it. And we'd also say that the mode, the one that has the most frequency, is this $900 value right here. And there's a lot more values on the right side of the mode than there is on the left side of the mode. And you see how it goes down really low over here on this side? That's called skew, and it is skewed to the right. So skew is described as a tail. The longer tail is on the right side of the mode, it is skewed right. And if the longer tail is on the left side of the mode, it is skewed to the left. And here's some examples of skewing to the right and skewing to the left. All right, so refer to the research cycle. Where in the research cycle is examining histograms located. So is it question, is it design, is it collect, is it analyze, or is it report? So obviously examining histograms is either in analyze or in report, right? So the collect and analyze portions of the cycle is where data will be gathered, organized, and presented in some way so that information about the data set is conveyed graphically, analytically, or both. So we're going to create the histogram after we analyze it, after we collect it, and that'll help us analyze it better, and it'll help us to report better with it. So what do you think categorical data means? Okay, categorical data. So think of it this way. When you put stuff into categories, you separate it by different groups of things, okay? So like, for instance, if you were examining a bunch of fruit, you would separate it by the type of fruit it was, whether it was an orange or an apple or a kiwi or a pineapple, and so on, etc. So that's exactly what it means related to word categories. So categorical data is information about how study subjects fit into different categories: Republican, Democrat, Independent, male or female, blonde, brunette, bald, and so on. So if that's the case, what do you think quantitative data means? Quantitative, think of that word. It's based on the word quantity, right? Quantity. That means it's a numerical value. So that's exactly there. Quantitative is related to the word quantity is information that is recorded numerically. For example, height, age, income, weight, all those things are quantitative data. So what do you think univariate means? Uni is a prefix that means one. Variate is a variation of the word variable. So it means there's only one variable. So we're only talking about one thing. Go back to one of these histograms right here. We're only talking about one value. The charges here and the age here. This value right here is not a value. It's just a quantity or a frequency that there are female cardiac patients of that age. And this is a quantity or the frequency of the number of female cardiac patients that are charged this amount. So quantitative data, there you go. Univariate means one variable. So information about one variable is recorded for each participant, for example, height, or charges, or age, and so on. Bivariate. Bi means two, so if univariate means one variable, bivariate means two variables. So this is information about two variables that are recorded for each participant. So in this case, for example, height and weight. All right, does a histogram illustrate univariate data or bivariate data? So the X values is the average grade per semester, and the Y value is the number of participants. Remember, we talked about when we're talking about frequency, that is a univariate value. So the number of students that got a 65 is 2, and the number of students that got a 75 is 7. Well, let's put it this way. In between 60 and 70 is 2, 70 and 80 is 7, 80 and 90 is 9, and 90 and 100 is 3. So this is obviously univariate data. One piece of information is given, each person's semester average, that is recorded for each participant. Since the semester average is represented numerically, the data are quantitative. It's not categorical. So would you describe the histogram as symmetric? Why or why not? So look at the mode. The mode is 9 right here, in between 80 and 90. We have 3 values to one side of it, and we have 9 values on the other side of it. We would say it's skewed to the right. To the left. Most say that the graph is not symmetric if they think that it does not meet strict mathematical definition of a line of symmetry down the middle of the graph. In statistics, however, it is very rare to find mathematical symmetry. The shapes of distribution are described in relative terms. This graph is, in fact, considered fairly symmetric, as the two sides roughly reflect each other. So think of it this way. This is 9 and 3, which is 12, and this is 7 and 2, which is 9. Yes, there are more values on this side than there are on this side, but the mode is in the middle, so they're about the same. Now, describe the distribution of grades for the class. Justify any estimates you make. In this case, the average is about 82 or 83. Well, how do we know? We know that there are values somewhere in between. We'll say an average is 65. We'll say this column is an average of 75, and so on. So there's 2 values times 65, 7 values times 75, 9 values times 85, and 3 values times 95. We divide that by the total number of values, and we can determine the number of values by counting how many are in each column and summing all the total of each column. So 2 plus 7 plus 9 plus 3 is 21. So the average is around 81.2. There may not be exactly 7 students with a 75 average, for example. The value represents a cluster of grades in the 70s, not 7 students with the exact same grade. So in other words, what they're saying is this column right here represents all grades between 70 and 79. This column represents all grades between 60 and 69. This represents all grades between 80 and 89. And this one, believe it or not, actually, it represents all values between 90 and 100. It includes that last value, okay? So, give you a little information about that. That's how that histogram is described. Now, consider this new histogram showing bus ridership at a local high school. The histogram is not symmetric. It is skewed far to the right. You know this because the distribution has a tail out toward the right side. What is happening with this population that causes the distribution to be skewed to the right? Now, first of all, let's look and see what the histogram is actually describing by the title. This is the age of students who ride the bus to school. This is the number of students. Students to the age of 14, there are 900 of them. Age of 15, there are 700. Age of 16, there are 300. 17, 200, and 18, there's only 100. So as we can see, the distribution is skewed far to the right. Y'all are good. Now, as the students get older, they get their driver's license and they start driving their school, and that explains why fewer and fewer of those students ride the bus. Or they ride with the friends. In addition, there may not be as many 18-year-old students at the school if some of them have already graduated. So let's estimate the average of students who ride the bus. This average is the center of the distribution. We're going to justify your estimate. So what we have to do here is we have to look, how many do we have in the 14-year column? How many in the 15? How many in the 16? How many in the 17? How many in the 18? We're going to sum all the total number of values up, and we're going to multiply the number of 14-year-olds by 14, the number of 15-year-olds by 15, the number of 16-year-olds by 16, and so on. And then we're going to divide by the total sum of all those values. So there are 14 times 880. I thought it was 900. 15 times 700. 16 times 330. I guess that's a little above 300. 17 times 180 and 18 times 90. And we're going to divide that by a total of 2180. So the average age is 15.04 years. So the average ridership is 15 years old. So suppose the histogram of this ridership looked like this instead. Data values that are distant from most of the other values are generally thought of as outliers. So this value over here that has 10 years old, that's an outlier. So what could have happened? Does this data distribution affect your answers to question 8 and 9? Well, of course it does, just very little though. Either there's some very bright 10-year-olds going to the high school, or there was a data recording error. So we have to investigate that particular collection of data to determine if there was a problem. You need to check the data to see if the correction is needed. If there really are 10-year-olds at the school, you need to refigure our average age and make note of the outlier. The histogram shown is at the top 20 men's 2-man combined bobsled times for the 2010 Winter Olympics. Only the seconds are gathered since each time began with 3 minutes. The histogram has a bin width of 1 second, meaning that the data is graphed in groups of 1 second times. So the bin width, this is the bin, this particular column, is a bin width of 1 second. The second ranges between 26 and 27. This one has a bin width between 27 and 28. This has a bin width from 28 to 29, etc., etc. Each time has an additional 3 minutes not shown in the graph. So everybody's time is 3 minutes and a certain number of seconds. And we can see from here, very few people had a time above 30 seconds. All right? Here's the same data in the last slide, except this time the bin width is 1.5 seconds instead of 1 second. Another way to describe bin width is the interval width. It is the interval between frequency bars and the graphical display. So now we do the bobsled times are between 26 and 27 and a half, and then 27 and a half and 29, 29 and a half and 30, 29, well, let's go back. 29 and 30 and a half, 30 and a half to 32, and 32 to 33 and a half. So in other words, it looks really symmetrical with this bin width. But if we go back, it doesn't look symmetrical at all, does it? The bin width has a lot to do with your analyzation of your data. Now, if you've got a lot of data points, it probably is okay to use large bin widths, especially if your data values number in the thousands or 10,000s. If you have very few data values, it might be best to go ahead and set it up with a smaller bin width. Because look what happens with the larger bin width. It makes it look a lot different, doesn't it? So I'm going to launch you with this. Before collecting your data to create your statistical histogram, ensure that the data are from a reliable source, or your analysis has no empirical value. So you make sure you have it from a reliable source, or your empirical stuff. You have nothing. There's no value to it at all. All right. Notice this little meme here. Database of useful information, 5,000. Databases of useless information, 500 billion gigabytes. Of course, that's right. Any type of information you need that's really empirical, you make sure you know what you're doing. All right, so that's it. There will be a lesson assignment in the Google Classroom by the same name. It is called Histograms. Please be sure you understand how to analyze a histogram. Go over this video again before you take the assignment, SAS 5 histograms. In the meantime, be blessed and be a blessing. All right.